Dzień dobry. It's great to be here, and it's amazing if you think that this is already 15th year that they're doing the GeeCON conference. I mean, Java is only 30, and so that's quite amazing. I would like to talk about stream gatherers. They have been added like in the preview version in Java 22, in 23, and became final in 24. Now, streams have been in Java since version 8, so that's like 11 years ago. And if I look at the audience, I think there might be a lot of you people who actually never had Java without streams. Is there anyone here who used Java before version 8? Oh, that's still quite a few hands, so that's good. So maybe you can remember back in the days when streams were added to Java. I was really excited when they came. I think we have been waiting quite a long time for it to come, because they were coming together with lambdas, so it was a lot of work, and it took around almost 2.5 years to get from version 7 to version 8. So there was a lot of excitement back then. And I remember working at a company as a consultant, and we were making some kind of an application, and the backend was written in Java. There was Java, there was Elasticsearch, things like that. It was some kind of legal editing system. And the front end back in those days, then Angular was still very popular, so that was written in Angular. And they used this BFF pattern, so a backend for the front end, to make requests easier. And this was written in C#, so the .NET guys were working on that. And we were sitting there opposite of the table, and we were saying, yay, Java 8 is coming, we're going to get streams, we're going to get lambdas, really excited. And they just looked at us and said, well, what are you talking about? We've had Link for ages, which is, their system. So it was really overdue for Java. But I think by now, I think everyone should appreciate streams, because, well, it is so nice just to do things declarative, right? You just say, okay, this is what I want to happen, and I don't care how it is happening. So this is what streams are all about. So, who am I? I'm a Java developer for more than 20 years. So yes, I've seen Java before version 8. I wrote a few books about it, but it's not all that important. What's on the calendar today? Well, we're going to look a bit at inner workings of streams, because having some knowledge of how streams function is good when you're writing your own gatherers, which we'll get to in a sec. Then we're going to introduce what are gatherers, and then we're going to do some live coding of a few examples. So we're going to make an alternative map, which is an easy stateless gatherer. Then we're going to look at a stateful gatherer, and then we're going to re-implement one of the new default gatherers. Let's start with streams first. I mean, we know what streams are, right? We had them, and you basically say, okay, I have some kind of a source, and this source can be anything. It can be some kind of a collection, it can be a stream, it could be a file. So almost anything can be a source for a stream. And then you have a number of intermediate operations. Could be 0, right? You could basically say, I have this stream, I'm going to do a toList, and that's it. It would be very inefficient code, but it is possible. But theoretically, you will have 1 to n intermediate operations. And then finally, we need a terminal operation, because nothing is happening until a terminal operation is being invoked. And all the time in your code, when you're defining this, you're just creating a pipeline, but no real code is executed. And then when we get to the terminal operation, then everything kicks off, because streams by default are lazy. So we get this terminal operation, and then it actually goes back and it says, wow, source, could you give me the first element that I need to process? So they're really a pull strategy. They're really pulling the data down. While if you take reactive streams, for instance, that's a push strategy, right? It's being pushed into the pipeline. So this is a pull strategy. And it is important to know that the source is processed part by part. So it isn't that the whole source, all the data in the source is being processed by intermediate operation 1 first, and when that is done, everything goes to intermediate operation 2. No, it takes one element from the source, it goes to intermediate operation 1, it goes to 2, and then until the pipeline completes. And then the next element is pushed. Now, there's a reason for this, because this will have some optimizations which are possible in streams then. One is operation fusion. You might define your individual intermediate operations, but the implementation actually is able to combine certain elements to make things more easy. And we will later look at some properties will actually make it decide if it should do the operation at all. Now, a second step is short-circuiting. It would be very inefficient if you have a stream of 10,000 input elements. You're going to do to the first operation, and then the second operation would be a filter. The first one could be a mapping. On this mapping, you want to do a filter, and then you say, well, I only want like 5 elements or something. So that would be very inefficient, right? Because you process way too many data. So short-circuiting and saying, you know, I'm done getting more data, that's really very efficient. The third one is size-based operations. And this is very important with parallel streams. We'll get to a second where we look at the split iterator. But size is really important, especially if you want to parallelize, because you want to have the threads to be balanced. And finally, the last one is based on specialization. Knowing what operations to perform, then the underlying framework can actually specialize some actions and do specific implementations. Now, there's 2 types of streams. There is sequential streams. And sequential streams, well, they basically say what they are. They are being processed by one thread from step bottom to, from begin to end. So a sequential stream is not parallelized, it's one thread, and there does its execution, which makes it easy to reason about. And it's also safer, because if we have things sequential, then we don't have any threading issues, right? Well, the alternative, of course, is a parallel stream. And if you identify a stream as being parallel, which you can do by the parallel keyword, then the JVM will say, okay, great. I will take threads from the common fork join thread pool and actually use those to create multiple threads. But how does it process these things then? Because, okay, you have one input stream and now you have multiple threads to process. So how are you going to divide the data? Well, this is something where the split iterator comes in. And we're going to look at the split iterator in a second. So you have this data. And then you say, well, I need to process it in multiple threads. So there's a specialized version of the split iterator in the Streams API that basically takes your data and says, good, I'm going to divide it in 2 balanced parts. And depending on the source, that's easy. If you have a list, then it's quite easy, right? Because a list is size, you know the size of a list, and you can easily split it. If you would process a text file, that's way more difficult because you don't know how many lines will be in there. Or if you would do something like a hash set, you don't know. There's keys in there, but you don't know the values which are behind those keys, how balanced they are. So the split iterator decides to split it up, and then if there's even more threads available and it thinks sizing is still needed, it will actually split itself up again and again and again. Well, again, it depends on the number of cores available, because your thread pool will actually have number of threads in there equal to the number of cores available in your system. Now, it might seem easy that you want to say, okay, threads, I'm just going to split it up, but you should really think about it, because if your input source is like 100 elements, there's no use in splitting it up and doing it in parallel, because the overhead of creating threads and later merging the results again will actually outweigh the benefits of processing parallel. So probably not a good idea. Then we look at the operations. Well, there are stateless operations on streams, in intermediate operations. The two classic examples are actually a map. Map, it gets an element in, you do some transformation on it, and you send out an element. But it doesn't know what came before it, it doesn't know what comes after it. So that's really a stateless operation. And the same applies to filter. You're getting an element in, you have some kind of condition that you want to test against, right? A predicate. And you test it and you decide either it goes through or it stops. So stateless operations. And then there is, of course, stateful operations. Typically, stateful operations, they need to keep state, so they're quite difficult to scale. Say that you have your string and you put the distinct element on. What you're saying then is, I want that every element in here is unique based on its natural key or based on the comparator algorithm I put in. So that really means that before it can actually produce an output, it has to know all the input, so it needs to buffer data. The same applies to sorted. If you say sorted to this stream, then it needs to have all the elements, and only when processing is completely done, it can actually do the sorting. So that's those are quite heavy operations. And then, of course, if you combine the things, if you would do parallel processing with stateful intermediate operations, well, that makes things quite difficult, right? Because then suddenly you're saying that it needs to keep the state, but it has to be somehow, the state needs to be protected because, it's accessed by multiple threads. So that is getting quite difficult. Good. To optimize processing of streams, the splitterator has a number of attributes. One is the ordered attribute. Lists, for instance, they're ordered because we know exactly, which element first, second, third, fourth. So sometimes it can be really handy to know if something is ordered. The other one is distinct, like I said before. If you're throwing distinct on something, that is really good to know. Take a hash set, for instance. If you have a hash set, with the set you already know, right? That's a unique key because we can't have duplicates. That's already distinct. So if you would put distinct on later, actually the input already knows I am unique. So it can optimize processing there. The same applies to sorted. If you have a sorted set or sorted map, then you don't have to request sorting later because the system already knows and it can actually skip this step. These are these internal optimizations it can do. Sized. Well, that is very important for the splitterator because if you want to process in parallel, it needs to split up the source, right? So it's good if it knows how large the source exactly is. Non-null. Sets, for instance, again, if there can be no null value, it's handy to have some optimizations in code there. Well, immutable is a bit the same, where you can actually say this data source cannot be changed. And finally, there is concurrent, which means concurrent access is possible. Again, parallel streams would really benefit from this. And subsized, meaning we've split up our input stream and we still know something about the size of the individual split up streams. Now these are used largely internal, but still we might be able to take benefits of them when we write our own gatherers. So what are gatherers? Well, we saw there's a lot of sources that we can already use. Anything can almost be a source for a stream. For the terminal operations, well, we already have our collectors framework. Everyone knows the collectors to-list or to-list, or you could say find first, or you could do min, max, average. Those are terminal operations. There's even a collectors API when you can write your own collectors if you want to. And actually, the gatherers API almost mirrors the collectors API. So they're very much the same with the same methods, as we'll see in a second. So the JVM language designers, they said, okay, we're going to do this, create this API so everyone can create their intermediate operations, because that's the one part we couldn't do yet with streams, right? Create our own intermediate operations. But they said, okay, are we going to supply any new gatherer operations, intermediate operations ourselves? And I said, yeah, we're going to do a few, but we could either make 1 million of them and really blow up the language, or we're going to just give an API. So we gave an API, and they added a few methods for us. There is a fault in there, and this fault gatherer, basically, it does an ordered reduction-like transformation. We'll have a look at it, how it works later, but basically, it just takes all the input elements and reduces them to one output element. There is the scan, which provides, it takes all the input and actually creates a larger output. There's the map concurrent, which is quite interesting because mapping normally always is like, you know, depending on how you define it, could be a sequential or a parallel process, but map concurrent actually does this. It takes, again, the normal common fork join pool and uses virtual threads to transform and do the map operations in parallel. And then there's a Windows fix if you have some kind of input source and you say, I want to have it like returned in smaller pieces, like say, I want to have them in groups of 2 or groups of 4. And there's a variant which is window sliding, where it actually moves the window a bit. Good. The gatherer API, which we're going to look at, is actually quite simple. It has 4 methods. There is an initializer. If you have some kind of stateful gatherer, you need to initialize the state, of course. Then we have an integrator, which is basically the part that's doing all the hefty lifting. It looks at the data and it decides, am I going to push it downstream? We'll get to downstream in a second. Then there is a combiner. If you have parallel streams, you just forked your input. So at some point, you have to combine everything together again. That's the task of the combiner. And finally, if all is done, but you're not done yet, then there is a finisher where you can do some final work before everything is passed on to the next stage. So, one more thing before we're actually going to look at the code then, and that is, there's this thing of a downstream. You get a reference to the downstream, and the downstream basically is just the next phase in your stream pipeline. So you have an upstream, but you don't have a reference to it, but you have a reference to the downstream so that you can actually push your data to the next element. Good. Then we're now going to look at the coding. Oh dear. Good. So let's see. We're going to look at the default gatherers first. So like I said, there's 5 gatherers. The map concurrent isn't really that interesting to look at. So let's just look at the other gatherers first. Is this visible for everyone? Ooh. Yep, okay, cool. So basically we have here a stream of gatherers 1 to 7, and we just say we're going to fold over it. So if we would run this piece of code, you can actually see that it does this reduction operation where it actually, ties everything together. The scan gatherer has something similar, same input stream, and if you would run this, it just say, okay, what I'm going to take the first and the second, and then I'm going to first, second, and third, and so on and so on. So it produces this output. Now, the window fixes might be interesting because later on we're going to re-implement this with a gatherer. This is now a default gatherer, so we're saying we have these 7 input elements, and I want to have them returned in batches of 3. So I get a 1, 2, 3, 4, 5, 6, and a 7. So you can really, split your source up if you would like to. Well, and the window sliding is basically a variation on the theme. Because you get 1, 2, 3, and then it drops the first element. You get 2, 3, 4, and it drops the second element, and you get 3, 4, 5, and so on. Maybe not the most sexiest of intermediate operations and things where you might think, well, where am I going to use those? But this is so cool with the streams or gatherers API, because you can actually implement your gatherers yourself. And I think that's what we're going to do now. So let's just close all the tabs and go to our first gatherer. And for our first gatherer, we're just going to do a simple mapper. And if you think about the mapper, it's quite simple, right? It gets an input element, it does some kind of transformation, and it outputs the transformed result. Now, for the gatherers API, it is actually quite interesting to have a quick look. Let me just do, because I think I'm just going to reset this. So we're going to start from the very beginning. So an integrator, if we look at this interface, it has 4 methods, like we saw before. It has the integrate, it has I should do so like this. So it has this integrator, it has this initializing of the state, it has the combiner, and it has the finisher. But of these, only the integrate method is actually required, because all the other ones, they're optional methods and they have default implementations. So that is good to keep in mind. Now, we're going to look at our simple mapper. So this is it. We have a stream of input values, and we want to do something here, something like, let's say, okay, we want to gather, and we want to say new mapper, and we want to provide a function here that it should execute, which we don't know yet, but let's say it's string to uppercase. And then we're going to do a toList. We're just going to store the result here to make it easier. And then we're going to print out the list. So there's a few things here which we're going to talk about in a sec. It'll get to here. Right now, it doesn't know where this thing comes from. So in our gatherer, like we said, it implements the gatherer interface. And as you can see, there's this default supplier, so it's not required. The integrator is required, and there's also default implementations for the combiner and the finisher. Hence, only the integrator is required. So, what we're doing here then is that we're saying, okay, I'm using the factory method of, which returns an implementation of the integrator. And the integrator has 3 elements. It gets the state, it gets the item to process, and a reference to downstream. And important is, an integrator always returns a Boolean indicating should I process more data or not. But we're not done yet with our code example here. So we said it needs a function, so we need to find something here, a private function somewhere that is going to do the mapping for us, right? So, and as it is final, we need to implement it in the constructor and do it like this, and that is okay. Now you see up here he's happy too now. So basically we have that part defined. Now we get to the integrated part where we actually do the work. So what we want to do? Well, first of all, we're saying, okay, we're going to create some kind of result, which is by applying the function to each element which is being passed down here. And then the next thing you only need to do is actually that we say, okay, downstream, you know what? I'm happy with this. I'm going to push it towards you. Oh, sorry, it can't push that one, of course. It has to push the result because it's of that type. Now, if you would run this, we are getting the result 1. Now, why do we only get 1 result? We expected everything. Well, after we pushed the element, we returned false here. And this false is actually telling to the pipeline processing, we don't want any more elements to process. You know, we're done. This is more than enough, and this is the short-circuiting we talked about. And later on in the next gatherer, we can see how we can actually use it to our benefits. Right now, actually, we want to process everything. So we're just going to say return true. And then you see the function is applied to all the input, and it's converted to uppercase, and it is outputted as a list. Now, still, this code isn't quite good, because what actually if my downstream tells me, because it has a mind of its own, I don't want any more, I don't want more data from you. It can actually tell me that with the push operation. The push operation also returns a Boolean, and this Boolean kind of indicates, does my downstream want more data from me or not? So the next phase, again, the next phase in our stream pipeline. So basically, code would be better if we would write it like this, where we let the downstream decide if more data should be processed. Now, on this downstream, there is actually an element that says is rejecting. And is rejecting tells, okay, does it say, I don't want any more data because it is either true or false, and if it doesn't want any more data, it is actually false. And once it has been set by the downstream, by the way, you can't reverse it. You can't say, oh, now give me more data anyway. Can't do that anymore. So that's actually how you can check up front if you should be short-circuiting. But writing code like this is actually quite good. Well, there's a few things in here which have nothing to do with streams, but I want to point them out anyway because they're new features in Java. One here is actually the import from Java module. because this is something new which is actually a preview feature still, but we can now import modules, and the idea is if you use, I don't know what util, something with collection classes. I mean, who writes programs where there's no collection classes, right? You always need to import them, but now with module imports, you can actually, if you use this module-based import, JVM was modularized in Java 9, it actually takes everything that is public in these packages, and it imports them automatically for you. So instead of having, I think I once looked this up and I came to like 83 imports I would normally have to do if I wanted to use them all, and I can use it just with a module import, and then it is much easier. The second thing here is this void main. Weren't we all teach that to start a Java program we had to have this public static void main string array args method, right? Well, no more, because there's now the simplified main method, because this was deemed too difficult. So this was actually deemed, and where they said, no, you know what? You can actually leave off the static part, or you can leave out the arguments, and the compiler will check, and as long as there is something still smaller, take out the arguments, take out the static, take out the public, but it will still run like this. A third part that maybe might have escaped your attention is actually this one here. I'm having 3 parameters in this method, right? I'm having, some kind of a void parameter. I'm having an item and a downstream. But I'm telling here, this is a stateless operation, so I don't have state. So even though it might be passed in, I'm never going to use it. And if you're not using it, then now you can use this underscore here. And it will actually say, okay, great, I know there's a parameter there. I won't even bother telling you about it, so it'll just work. And actually, you can make this code. Oh, actually, no, there's one more here. There's this print line here. Well, this isn't the system out print line we're all used to, because that is something in a different class. This is actually the io.print class. And here I had to import it, which I still preferred over writing system out print line. But if I would change this code and I would say, you know what, I'll take away the class name. So now we have a Java class without a name, technically, or actually there's no outside class, and it always used to be, right? We always needed that. You can actually still run it, it'll still work. So you can run your application with your main method not being in a class. It's then an implicitly declared class, which there can only be one of. And in such situations, I think even this import statement here of the print line isn't required anymore, because that's automatically imported then, if I remember well. Yes. So these are some changes to Java, which are besides of this part, but Java is really changing. So thought it would just be good to know. Good. Let's move on to our second gatherer. So we had this stateless gatherer, which was cool, but we didn't really have any state in there. So let's do something with state. And we are going to do this limit operations. So basically what we're saying here is, okay, I only want to process like 3, 4, whatever, a subset of all the data. So we need to create a gatherer for that, and now we need to have state. Well, one thing you can see here is I'm not declared a class, I'm now actually made it a static method, which is a different way to use them, and I'm going to do this off sequential. Well, off sequential basically says, okay, this stream is definitely a sequential stream, so it won't have parallel processing. And with limiting, it makes sense, because if you say I want to have, like, I don't know, 5 threads, and they're processing, and you say, oh, got a limit of 4, so how is the system going to find out, right? So it makes sense to use at least this part, in a sequential way. Now, first thing we need to do when we define this gatherer now is that we actually need to initialize its state. Before we didn't have state, now we're going to use state. In this case, I'm just going to create an atomic integer. Technically, atomic isn't even necessary because, you know, it's sequential, so there won't be any race conditions. But let's just say that we do it like this anyway. And the way we want to use this stream, to give you an idea, is say, okay, I'm going to gather, and I'm just going to say limit to, let's say, 3 elements. And again, do the same thing, do the toList, and print out the results. Great. So this off sequential, as you can see now, it has 2 elements. It has the initializer, which we just made, and it still needs the integrator. So it could simply, if you wouldn't have to do anything, you could actually say really downstream push with your element, and actually you would be done. That would be very elegant, right? Unfortunately, that's not what we need to do here. We need to implement some logic. And isn't IntelliJ great? I practiced this a few times, and it really remembered what I did. So what we're saying here, good, we just going to increment our integers, say, okay, well, we were 0, now we're going to 1, and is that still below the limit that we wanted to? If so, I'm just going to push the element downstream. Oh, that's too bad. There we go. That's great, right? Because, okay, we're still with the limits of our processing, and then we're just going to say, oh, great, push downstream, and then just return true, meaning it will process all the elements. And if that isn't the case, then we should just return false. And there you see it processes 1, 2, and 3, and it skips the processing of the other elements. So that's where we have a stateful gatherer. Again, you need to initialize the state, and you need to guard it. If you decide to do things in parallel, actually the state isn't shared. Even if you say, okay, we're going to run this one, because default, if you do the integrator off, you'll get a parallel stream. So you really have to do off sequential to get a sequential stream. If you do it in parallel with your gatherers, your state will be in individual gatherers, and you can't combine it. So then technically you have to wait until you get to the finalize method, where you can do your final operation, and there you then have to merge the state again, or in the combiner method. So that means you're really going to process. So normally, gatherers in parallel could cause certain difficulties. For our final example, we are going to look at the window width method. And basically, what we're saying here is, we just saw this window fix gatherer where it says, I want to have an input source, and I want to have a split in different parts. Now, how do we go about that? We're creating here a window width method, whatever you want to call it, and we say we're implementing a gatherer. It actually takes in an element of type T. Its state is in the list of type T, and the output is also a list of a type T. So first, we need to decide how we're going to work with this. We're going to need something to hold our state. There's a number of lists or a number of elements that we're getting in, and it could be any type. So we're going to create a new array list here that will hold our state. And then we get to the integrator part, and this is where things then get interesting, because now we're not going to just push things downstream right away. So what we're going to do, we're getting in the state again, which is the list of type T, and we're getting the item and the downstream. And here we can basically say, okay, state, you know what? I'm just going to add you this item that we have, but I'm not going to push downstream yet. I think I'm going to do just check if the item size, sorry, of course not the item, the state size, if that is actually equal to the number of elements that I want to have in every part of the list. And I'm just going to put it in hard now, because right now we didn't create that part of the code yet, which we should really start with. So we're going to define a private final, and we'll call it window size, and then we'll just create this constructor, and we'll set here the window size. So if we set it up here to 3, then window size will be 3. So now we can compare the size of the elements that we already buffered internally. We can compare that to window size. And if they're the same, that means our buffer is full. Well, then we get to the point that we say, okay, downstream, this is for you. So I'm going to push you. And then we're going to start all over again, right? We process the first batch of elements, and then before we start the next, then we actually need to reset our state. So we're going to clear it out, and we're just going to return true here. Now, if you would implement the code here, then we say, and we'll do the 3 elements. We'll do the to list. Oh, sorry. And of course, store the result and print it. And we keep on hanging to this print line method. Right, now if we would run this gatherer, which seems to be okay, the result might be a bit unexpected. We get 7 and 7 in 2 batches. That's not really what we expected, right? Because we wanted to have batches of 1, 2, 3, 4, 5, 6, and 7. Well, it turns out that having this code here is not really working, because we're saying, oh, wait a minute, we're pushing this data downstairs, it's still an object reference, and then we're clearing the state, and that somehow confuses the framework. So what we're going to say here is, okay, we're going to return a new array list with the state, and then we're going to clear the state. And this should really make things look better. And you see, it's already better. We got 1, 2, 3, and 4, 5, 6. Still, we're missing one part, isn't it? Because what happened to 7? Before we had 2 7s, now there is none. Well, the system processed and said, okay, 1, 2, 3, they're processed. And then it did 4, 5, 6, and it was pushed downstream, right? And then it got 7, and it stored 7 internally, and then no more came. So we never had a chance to push this 7 element downstream. And especially for this reason, there is this thing called the finisher. And the finisher just gets 2 elements. It gets the current state, and it gets the downstream. So if you would implement this code here, and we would say, if not, state is empty, we can just say, okay, great, then we'll push the state downstream. And we don't need to care about if it says, yeah, I'm accepting more data or stuff like that, because this is the final operation we'll ever do on this downstream. And now if we run it again, we see 1, 2, 3, 4, 5, 6, and 7. Great. Let's see if there's anything more here in the demo. We had this demo, we had the alternative map function, we had this demo. No, I think that we actually got to the point of questions. Oh, there's one thing actually I do want to mention, because you might think, am I really going to use this gatherers API? Again, you can make your own intermediate operations, and there is this framework made by Mr. Ginsberg, which is called Gatherers for J, and you can actually see he created a lot of these intermediate operations. And this is exactly the reason why we got an API and why they weren't added to the standard JVM, because everyone has their own ideas, and you can create your own, make a library, and distribute them, just like any other thing. Well, I guess no more beating around the bush. We have to do the questions. Are there any streams using scenarios that can lead to memory leaks, and what should we pay attention to? Well, that's a very good question. When you have stateful gatherers, that could be the thing, because then you're maintaining the state. So it's really up to you what you're doing there. And as you could see from the first one, from the last example, if you're not careful with processing all this state, things could go wrong. Could there be memory leaks? Your state is normally internal. That means it's defined somewhere in your code. And once that code completes, actually memory should be gone. So normally there shouldn't be anything that causes these problems. And since when is this Java version available? Well, it was previewed in Java 22, then got another preview in 23, and actually became final in 24. So it's now in the latest Java available. So you don't need to do anything with preview anymore. And the interesting part is that during all these previews, there was never any change to the API. And of course, that was basically because it was based on collectors. So it was already kind of developed. But it's quite amazing to see if you compare this with structured concurrency. There is a talk later these days on structured concurrency. Well, that has really changed a lot through all its incarnations. Streams, gatherers is really still the same. So splitter attributes are suggesting, but don't enforce unwanted behavior where it's not possible. Yeah, from your gatherers, you can't really change these attributes because, these attributes, they're used internally, but they're just for optimizing things. Again, for instance, if you would do a map operation, say your stream is sorted and you do a map operation, then what this map will do in the end is say, oh, if sorted attribute was on my stream, I'm going to turn it off. Because suddenly, right, you had some input that was sorted, and you create new output, so it's definitely no longer sorted. And that's the thing, how these attributes are being used under the hoods. The for limit together, you're returning true false regardless of downstream push. Yeah, exactly. I just did it because I'm already running out of time now, but you're right. You should always do return downstream push, and that will indicate whether there is more demand for new elements. Have there been any VM JDK optimization to reduce transient allocations when using streams? I have no idea. So I can't say this. I don't know. Sorry. And with that, oh, there's more questions now. What about memory limitations for streams? Yeah, it depends a bit on what you're doing. You can have, again, streams. They also work on files. Then you can actually be quite efficient. But just if you have large lists and you have them in memory, then there is limitations, definitely for sure. So, but gatherers doesn't really change that. So, I think that's it. So I thank you very much for your attention and enjoy the great conference. Oh, if you want to filter, oh, it's gone again. You kicked it out, huh? It was too late. Okay, well, enjoy lunch.